Hi, my name is Jasper Brown. I'm a PhD student at the ACFR, currently in the final stages of finishing a thesis on soft tree fruit varieties. So as part of this research, we developed and tested an autonomous harvesting platform for plums. And today I'd like to take you through some of the lessons we learned during this research and what implications this has for harvesting less widely addressed crop types. So let's start with what is a soft fruit. While there's not a black and white definition, these are generally fruit which bruise or tear easily, like plums, pears, and most types of berries. A tree crop is what it says on the box. They grow on trees. Very roughly, these two properties correlate with the horizontal and vertical axes on this slide. Some crops are very easy to harvest without damaging them, things like wine grapes, nuts, and hard-skinned fruit. Others are difficult to harvest because of their soft skin, like plums, or ease of bruising like grapes. Separate to ease of harvesting is how challenging the environment of harvesting is, so that's this y-axis. Greenhouse-grown crops have less variation, they have well-controlled lighting, well-defined obstacles. That's not to say these are easy to harvest, they're not, and this graph is only illustrative, but there are fewer ancillary problems around power supply, data links, navigation, actuator reach, and motion-based design to solve for this end of the y-axis. So all those extra robotics problems that you have to deal with during harvesting. Outdoor tree crops sit down the bottom here, so there's complex obstacles. There's things like rain, wind, and direct sun, which may affect both your hardware and your perception problems. There's also a lack of data link access and lack of available power, so you have to generate your own power, for example. So in addition to where it falls on this graph, every fruit and vegetable will have its own quirks. So things like mangoes have acidic sap, which can damage the mango skin and even burn workers. Truffles, really hard to find, therefore difficult to harvest. Up in the top right here we have row crops, so they're very robust to harvesting, and they have a very easy harvesting environment because they're planted in nice straight rows. They're very easy to spot and remove from the soil, basically. So specific market conditions will also impact where a crop falls on this graph. In Australia, table grapes are picked by hand to avoid bruising, whereas wine grapes can mostly be harvested mechanically, as well as any grapes for jams and things. So harvesting the right-hand side of this graph has been progressively automated. So decades ago, row crops were mechanized, nuts have been mechanized using shaker mechanisms, wine and jam grapes have been mechanized for a while now, but we're starting to see more and more of these shift to the right on this graph. So the current research frontier, if you will, sort of goes through here somewhere, where there's a couple startups working on apples. Capsicums have been extensively researched. Strawberries in particular have some startups focusing on those, as well as other types of berries. And we're slowly moving this line sort of left along this graph as we get into more challenging and less common crops being commercialized. And each new variety that we look at brings new lessons for the field of agricultural robotics. So in my research, I've focused specifically on plums as an unaddressed soft fruit variety. Currently, this is what a soft fruit harvesting operation looks like. With experienced pickers bagging over 5,000 an hour, that's a huge amount of expertise and dedication that any potential solution has to compete against. However, the challenge for growers is finding that experienced labor, which is in short supply during harvest seasons. So there is a place for robotic systems to augment these workers in the short term by picking easy fruit and leaving harder cases for the more dexterous and responsive humans. To understand what technologies are required to get to that point of autonomous soft fruit harvesting of easier cases, we built a harvesting development platform for plums. This was then tested on a commercial plum crop down in South Australia. So in this presentation, I'd like to take you through briefly how that development platform works and lessons we learned from building and testing it, both in terms of robotic techniques and implications specific to soft fruits. On this development platform here, we've got a UR5 cobot articulated arm with an air-actuated soft gripper mounted to the end of that. Also on the end of the arm is a D435 RealSense RGBD camera. So that's our primary sensing modality, which is used to detect and localize plums. Those are then picked using a fixed motion sequence. So we localize the plum, we apply a motion to the arm, which goes and picks it, and everything is self-contained within this small trailer. That allows the whole platform to be towed by one of our robots, or by a car or buggy on the farm. It includes a generator, air compressor, general purpose computing, as well as an embedded deep learning inference computer specifically for object detection in real time, as well as hardware to support the arm and gripper. So the first step in picking any fruit is spotting it, and on the left here you can see our perception pipeline. We use the on-arm RGBD camera, which you can see there, to detect fruit in 2D imagery. So we get an RGB image, we run an object detector over that, that gives us bounding boxes around our fruit, or hopefully bounding boxes around our fruit. What we found was you can take this bounding box, apply it directly to the depth map, and get a depth value for each fruit, so one number that is how far away it is. But that's generally not very good, and that's because there's things like leaves in the way, so you may pick up pixels that are on the leaf, or you may pick up pixels that are on the background, and a lot of these fruit are very highly obscured. So that one, for example, the depth value is going to be completely wrong. There's a big leaf in front of it. What we do to remedy this problem is, as a second step, we apply a very lenient HSV, so hue saturation value filter, over that RGB patch. So that very small part of the image gets filtered, and that extracts pixels which are expected to be on these plums. And that works well because plums are easy to distinguish in the HSV space from the background leaves and background sky. And because it is such a small patch where we know there's a fruit, we can use a very lenient filter, which is great. So we take those masked pixels, which belong to the fruit, all these white ones, we apply them to the depth map, we apply the bounding box extent as well, and then we take the median value of all of these pixels from the depth map, so they're depth pixel values, take the median, and that gives us the 3D position of the fruit once we project that back into the world frame. So that gives us the 3D pose of each of these fruit on the trellis. We also have a pose tracking camera on the trailer, which you can see there, which allows us to put everything into a global inertial frame within the orchard. So there are a couple of challenges at the perception step that go hand in hand with eye-on-hand harvesting. The main one there is the change in scale as the camera goes from viewing the whole trellis, this is a typical image of that, so what it looks like as it's driving along, to going and picking one of those fruit. You want guidance from the camera right up until the picking point, which means these fruit get very large. So you can see one here as it gets closer, they get larger and larger, and eventually they'll take up the entire image frame. That also leads us to changes in exposure of the camera. So far out there's a lot of light coming in. As you get closer and closer, it gets progressively more shaded by the leaves on the tree. So you do need to adapt your camera exposure. And here is an example frame of where that's gone wrong, of an overexposed frame. We also do picking during nighttime under artificial light. So that totally changes our illuminance, our exposure, our color balance. And it also means you only see the frontal plane of the trellis, so one of these rows, whereas during the day you can see the row behind it quite clearly. At night we also get issues with things like blurring becomes more of a problem. So there's all of these challenges around perception, specifically with eye-on-hand harvesting setups. In order to look into this problem a bit further, we developed both a daytime and a nighttime ground truth dataset to test various object detector architectures. And one unexpected issue we saw was pretty poor performance by some highly regarded architectures. So we trained 5 different object detectors, and shown here is an example, it is just illustrative, between an embedded YOLO V3 model on the left and a RetinaNet model on the right. So both are state-of-the-art frame-by-frame RGB input models using default training parameters, and on paper they should perform pretty similarly. The YOLO model is converted to run on embedded hardware, whereas the RetinaNet one is not. So that will explain some of the difference. So here's the actual data behind that comparison. We've got precision recall graphs for each of those models, both with and without transfer learning. And there's a few different takeaways from this little study we've done. One is that performance on our harvesting specific data sets did not match the rankings of each network on wider computer vision benchmarks, so things like COCO. That means various object detector architectures should be tested for performance in agricultural robotics applications, rather than assuming established rankings will hold for these applications. This even varied between the day and night data sets. So the best network during the daytime data for looking at plums was not the best network architecture for the nighttime plums. Second, we learned that network architecture selection was similar in importance to applying transfer learning. Once the fruit are detected in 2D and they've been projected to their 3D positions, we run an extended Kalman filter to filter that incoming position information, which is applied to all incoming frames. And at the same time, it checks if existing fruit should have been seen from the current camera viewpoint. If a fruit should have been seen and is not, it gets flagged as a false positive, and it will be removed after several flags. This persistent filtering helps to eliminate a lot of the object detector false positives and negatives, which is important because a lot of fruit are really difficult to see. They're obscured in many viewpoints, and they do move around as well, so they can cause false positives in that way. 3D positions get registered to that global inertial frame and can be tracked throughout the orchard for counting and yield estimation. This means whenever we want to harvest one, we can go and look up its position, which is stored in the filter state vector, and it will be the most up-to-date estimate of that fruit position. On this slide, you can see the internal system state during picking. The trailer is that green obstacle, with the red sphere showing the arm reach, and the blue box is our region of interest, so that's where we actually attempt picks. The current arm state is shown rendered. The orange arm state is the planned motion to go and pick a fruit, which you can see in the top left there. Each of these white spheres is a fruit position, and this yellow plane is the trellis obstacle, so we don't go beyond that. So that's the perception pipeline, essentially. Now I'd like to take a moment to look at the most important overall challenge that we identified, which is the mixture of hard and soft obstacles and how you plan under that. So to understand the mix of obstacles, you first have to know about the growing environment. 2D planar trellis, which is also known as a fruiting wall trellis, was chosen by the grower we work with for easy mechanized access. And it also turns out to be really good for automated applications as well. All the fruit are very accessible when compared to trees, and the structure is a lot more regular than even a V trellis. So you can see that in the footage here from one of the field trial nights. It's all a nice flat plane of fruit. But even with 2D trellis, there are still irregular and hard to spot obstacles. Fundamentally, when reconstructing the scene using robotic sensors, the problem is going to be differentiating between which obstacles are soft, like leaves, and can be pushed through, and which obstacles are hard and will damage either the robot or the tree. One scenario is we misidentify rigid obstacles as soft and we run into them. Using the arm torque sensing, we can detect and recover from these collisions, but it's bad for the tree, causes wear to the robot, and it slows down the whole process of harvesting. The opposite case is misidentifying soft obstacles as hard and concluding that fruit cannot be reached when in fact they can. So both of these outcomes are bad, but differentiating between hard obstacles, shown in red here, and soft, shown in blue, is a really difficult problem because tree trunks and trellis wires are often obscured. So there will be hard obstacles behind soft obstacles, which means it's not always possible to identify them. Our approach, therefore, is not actually to solve the problem of differentiating them, but by using careful system-level assumptions, we can avoid the issue altogether. With these 2D trellis rows, tractors, trimmers, and spray units will travel very close to the trellis plane throughout the year, and they'll break off any hard obstacles that stick out too far. So these are mechanized farm operations that have to happen anyway. And by virtue of these large machines rolling up and down the rows, we get this green area, this green region on the right, which is guaranteed to not have any hard obstacles in it. So within that region, we can use complex arm motions at full speed, we can use generic arm motion planners. As we move closer to the trellis, this yellow region will have a mix of obstacles in it. So to minimize collisions here, we use linear approach motions, where the gripper will move perpendicular to the trellis from the green region straight in. It will grab a fruit and then it will retract back to the green region before it goes to drop it. Within the yellow region is this red line. So that is the trellis plane, and it's certain to have rigid obstacles like the trellis wires within that plane. We still need to grab fruit within the region, and the solution that we came up with to that was to design a gripper that has soft components extending beyond a certain region. So the first gripper we looked at was this. It's quite complicated, it has embedded sensing, it has a lot of rigid components, and it's quite large because it has many degrees of freedom and a lot of sensing embedded in it. The problem is that size and rigidity was leading to a lot of collisions when trying to access the canopy of the fruit, and it was also very hard to plan for and to actuate for because it was too complex. So we vastly simplified the gripper design in the next iteration into a parallel finger design. That works great in lab tests. It's tendon drive, single degree of freedom, very simple, fast and easy to build. But those issues with running into hard obstacles persisted. So it's a question of how do you access those fruit that are beyond that red plane without running into things like the trellis every time you try and do that. And the solution we came up with was this, which is a gripper that utilizes soft components beyond a certain region. So everything on the right of that dashed line is a soft component. And when that runs into a trellis wire or a trunk or a trellis post, it will deform, and it doesn't damage the tree. It doesn't lead to a stoppage of the harvesting process. It does cause wear and tear to the soft components. So that's one thing that we're still working on at this point. Also in this, you can see the RGBD mounted camera. So that's the eye on hand camera, and the wide angle embedded camera for visual servoing. So by using that soft finger gripper, that red trellis plane, we don't actually have to have any of our rigid components. So the gripper cup stops at that plane, and the fingers can reach just slightly beyond that to harvest up to the midpoint of the trellis, so that we can access all the fruit in the tree without problematic collisions. We looked at a few different motion strategies for picking, and this one shown here is based on actual human pickers, and it includes a rotation motion and then an angled retraction. And the reason for those two steps is that if you pull the fruit straight out from the tree, it will lead to a stem pullout. And stem pullouts are bad because they allow a route for ingress of bacteria into the fruit. So often if there is a stem pullout and it damages the fruit skin, that will need to be thrown away completely, otherwise it could spoil the whole batch. So you'll notice that as part of this, there's not actually a visual servoing approach controller running for the final stage when it goes to grasp a plum. We trialed that in the lab and it worked really well. It was very effective on the simulated lab trellis setup. But when we went to actually apply that in the field during field tests, we found that for two reasons this was not effective, and it was actually counterproductive. So because the plums are very close to the branches and the stems are very short, especially compared to fruit like apples, where other research groups have identified pendulum behavior during picking as a real problem, plums don't move that much due to the short stems and proximity to branches. The other thing is, as the camera gets closer, even that wide angle camera within the gripper is very often obscured, which will lead to a loss of tracking and can throw off the controller very easily. After developing that prototype and testing it in the lab, we then ran a week-long field trial in South Australia, testing it on a commercial plum crop. So we attempted to harvest portions of that crop, and we recorded both the overall picking rate of the platform as a whole, and we also looked at specific studies on the picking motion type, the gripper type, and a few other factors like the object detector. So that about wraps up my talk. To recap, the key lessons that we learned during this work were the ineffectiveness of the visual servo and controller on plums, the importance of the harvesting motion type selection to harvesting fruit without damaging or dropping them, the variation in the ranking between object detector performance on our task and more general computer vision tasks, and how persistent object tracking could be used to overcome that, and then how to solve the hard and soft obstacle planning problem at a systems level through those various techniques. In terms of future work, we'd like to identify fruit to exclude from picking, whether that's because they're unhealthy or unripe or too difficult, so they may be impossible to pick with our system. And finally, improving soft component robustness, so making those soft gripper components last a lot longer. And finally, I'd just like to thank all my colleagues who have helped and contributed to this work.